Yes, hello everyone. My name is Mugabe Samuel, together with my colleague Simon Onen, and we shall be taking you through our paper of explainable deep learning for intelligent transport. The case of our study is mainly bike sharing platforms. Here, intelligent transport mainly means transport that is coordinated and smart. Yes, so this is our table of contents, but allow me skim through that very fast. Now, bike sharing is becoming popular around the world because it's affordable, it's healthy, eco-friendly, and you know that the world leaders are talking about climate change. So innovations around there are so much welcome. Now, in bike sharing, predicting hourly demand is very important because it helps docking stations cope with unmet demand. Unmet demand means losses for the company, and the company does not want to go there. Now, machine learning is giving computers to learn a task without exclusively giving them instructions of how to go about the task and not intervening so that they can identify different patterns within their learning. Now, different machine learning models have been developed around demand forecasting in bike share, but most of these are overwhelmed by the big temporal data that comes in. And it is from here that deep learning comes in. Deep learning thrives on big data. Okay, so those are our keywords. Now, for our computational problems, we came up with 3 computational problems, whereby we have vanishing or exploding gradient. Vanishing gradient is where the loss function becomes very small during back propagation, whereby the earlier layers end up getting little updates. And also exploding gradients is where the loss function is very exaggerated, hence affecting the model. But all this, we overcame it by using and opting for GRUs. Our second computational problem was model interpretability. Deep learning neural networks are very complex. So we want to add interpretability so as to know the feature importance, what features were important during a prediction, and so understand how the model comes up with certain predictions. Our third computational problem was hourly demand, where we are forecasting the hourly demand, and we opted for sequence-to-sequence models, where we realized that GRUs are faster, but however, LSTMs are better for complex tasks. Now, for our problem statement, remember we are looking at demand forecasting, and in this demand forecasting, you're getting data from different sources. It's heterogeneous data. You're talking about temporal data, spatial data, you're talking about unknown client behaviors, and all these have to be put together to come up with a prediction. For our research contribution, in our research, we are mainly improving interpretability and transparency of complex deep learning models, whereby we bring to light a trade-off of complexity, but the model is accurate, hardly interpretable, but it's accurate, versus the model being a basic model, but then highly explainable, but the performance is a bit low. Whereby in our research paper, we want to strike a balance between model accuracy and interpretability. This is our dataset description. The data came from digital bikes at Makerere, and it's using a system where someone logs onto the application, requests for a bike, and the agent replies on the other side. Now that transaction is logged in the system, and this is the data that you are seeing there. We also had the weather data set that came from Makerere Meteorological Center, where we had total rainfall, dry bulb, wet bulb, humidity, and wind speed. Now this is some of the heads of our data. We continued with our exploratory data analysis, and we looked at the correlation heat map, where we observed some correlation in let me say use a male and unknown gender, and also wet bulb and dry bulb. We also observed some correlation there. This is further, this is some more weather data, EDA with the weather data that we observed also on the time series features. We did a correlation heat map. Now you realize from the graphs you're seeing, the graph on the left, top left, you realize say that is the popular station, and the popular amount used is 500 shillings. Our data is running from March to June, as you can see there. Yes. Then also for the weather data, we have humidity, total rainfall, and mainly these are normal patterns, as you can see. Allow me call my colleague to come in from here. Yes, Simon.
Thank you, Samuel. In our methodology, what we're trying to achieve was to do a three-step approach where we broke down the steps into those three categories where the step one, we're looking at how we're acquiring all this data, the trip log data, and then also the weather data, and then conducting some pre-processing where we first retrieve the data sets and then combine them. Then after we do our exploitative analysis, where we also analyze all the data sets individually. After that, we develop our models. And before that, we prepare our data for each of those models in the respective way the models expect the data. And then we go ahead and do hyperparameter tuning, which we're using the Bayesian optimizer for all the models for uniformity and comparisons. And then we go ahead and do model explainability, where we use Sharp and Lime. We further go ahead and also compare the performance of these models via their accuracy and explainability. Yes, continue on the next slide. Yeah, when you look at our model architecture, what we wanted to achieve was there are several deep learning approaches where research studies have showed that researchers do this in two types, where some opt for having time series data sets, and then others use some feature engineering and extract the variables from the timestamp to come up with individual variables like the year, the month, and then the time of the day or specific hour as individual features, and then they train the models. So we wanted to have a comparison between these two approaches, where we look at the comparison where you're using an entire data set with features, and then also look at a comparison where you're only looking at the time series approach, where you consider the timestamp and the target, and you come up with features, let's say hourly features that are in sequences that lead to the final prediction. Go to the next slide. So we did continue and conduct the training on our first deep neural network, where the performance showed us on the trip log data. As you can see on the left, the error goes on decreasing as the training continues. The error in the training and the validation set merge at almost the 19th epoch. However, on the right, when we went ahead and inspected our tuned model that was trained on the triple log data, we realized that below the 7 mark, the error had reduced. However, when you inspected further, you do realize that the validation loss keeps on increasing as the train loss keeps on decreasing towards 0. The next slide. So when you try to see the performance of the models when we compare the predicted and the actuals, on the top left you can see how the model performed on the training data set, and on the right how the model performed on the validation data set, where we see there was a huge variances towards the negative. Then at the bottom left, we went ahead and tuned the triple log data set, where we clearly saw some similar way of performance, however, not that convincing. Then on the right, after tuning the triple log data, we clearly saw some bit of performance showing us zeros according to variances, where in certain epochs we're hitting 0, which means the predictions were actually accurate. So we went ahead Next slide, please. We went ahead and compared the performance where we trained a model after enhancing the dataset with weather features, where on the left we clearly saw the performance was trying to catch up due to the temporal variables found in the weather dataset. We clearly see that the error margins, if you compare the scale of the loss, are now less than 1.0, where we clearly see the model is performing better. So when we went ahead, go to the next slide. When we went ahead and plotted the performance, we clearly saw a better performance on the both on the training and validation data sets. However, on the tuned model, it even seemed better, where we realized that maybe during the data merging, we saw that maybe they would have made maybe an issue there. That's why we want to go back. Then on the next slide, this shows us that we merged. In the previous slide was showing us we had merged only on the date. So we went ahead and merged using also the time. That is how now the performance on the bottom right here shows us that though the model was performing better, it is still better, but not at its optimum. Next slide, please. Next slide, please. Next slide, please. Next slide, please. Samuel, next slide.
I'm on the next slide.
Next slide, please. So when we compared the performance of the models, we realized that the model that was trained on the dataset at hinders performed better than the other model. So we went ahead and did the time series approach, where we considered the timestamp and trained 4 models, where we realized that the best performing models were actually looking at the LSTMs. Next slide. So we went ahead and tuned the models to clearly understand whether our justification for the best performing model was correct, where we realized that on the tuned model that was trained on the sequential deep neural network, realized that the loss function and the validation was kind of constant. On the RNNs, it kept on increasing. Then LSTMs, it kept on decreasing. And then on the GRUs, it was also constant with a little bit of spikes within after immediately between the 20th and the 30th up epoch. Go ahead, please. Next slide. So when we looked at the performance of the predicted and the actuals, the variances were clearly there, meaning that the dataset we used to train these models had very few samples, which were around 1,200, meaning that there is need to investigate this further while comparing a huge data set, because whenever you do some sort of groupings in sequences, data tends to reduce. So when you compare all the performances, you can clearly see that the RNNs in the validation data set didn't actually pick anything because of that negative. However, in the training data set, they clearly showed us that it fitted well, clearly understanding all the data points. And then when you compare with the GRUs, you can clearly see at 0.3, they did not perform better. That brings us to the point where Sam will come in and explain for us explainability as we wrap up.
Thank you so much, Simon. And now on the bit of explainability, we considered global and local interpretation. Now for our local interpretation, we were using LAME explanations, whereby you see that the top features of LAME, there is month, user gender, amount, day, and duration requested. This is on a local scale for a single observation. But then when you use sharply additive sharp for the global interpretations, you realize that other features are the ones that are important to the model predictions. You can see that agent's name had a high impact on the model, whereby it was affecting it negatively. Now, this can be something to consider by the administrators of the system. Then you can see that origin had high impact points also on the negative. So the origin was affecting the model negatively. It was pulling it to the negative side. Same applies to month, and then wait bulb and start of the day. Now, this explainability, it helps us gain more trust, trusting the model, users of the model trusting it, and also understanding why it makes certain predictions. This is Lime. Had covered that. Now, for our conclusions, we realize that time series approach using deep learning methods like LSTMs and GRUs, they minimized errors and improved accuracy. The other observation we made is that that the weather data, when you add more features to the data set, features like weather data, they provide us a platform where you can get explainability of the model and understand why it's making certain predictions. Then also we understood that time series models, they demonstrated a superior predictive performance as compared to the other models, to its counterparts. And also in here, we observe the trade-off of model accuracy versus interpretability. But for our paper, we are pushing for a balance between the two. Okay, so in our acknowledgements, we would like to acknowledge DigitalBikes for granting us access to the dataset for educational purposes, and also Makere Weather Station, and also our supervisor, Dr. Galiwango Marvin. Other than that, thank you so much for listening.